So last time we left off talking about entropy, enthalpy, and Gibbs free energy. And we said that there are two conditions which are always or never for delta G. Remember we said delta G is negative for all spontaneous reactions. The second law of thermodynamics says for any spontaneous change, delta S of the universe must increase. And delta G and delta S of the universe are related, but opposite signs. So delta G must be negative for a reaction to be spontaneous. Whew. So when a reaction is exothermic and it creates more disorder in the products than the reactants, so when your delta H is negative and delta S is positive, delta G is always negative. That is always and forever a spontaneous reaction. No matter the temperature, that is always and forever spontaneous. Conversely, when you have a positive delta H, so it's an endothermic reaction, and you're creating more order in the reaction, your delta G is always positive. That is never spontaneous, no matter what temperature. But the two interesting conditions are when the signs of delta H and delta S are the same. When both delta H and delta S are positive, or both delta H and delta S are negative. When the signs are the same, the conditions are interesting and temperature dependent. So this reaction says it's endothermic, more disordered products, spontaneous at high temperatures. So entropy times temperature is going to become an important factor. When the reaction is exothermic and creating more order, we say it's spontaneous at low temperatures. So this factor is our more important one. Well, let me explain some more soon. So if we're going with our first case scenario of endothermic reaction and positive delta S reaction, this term very rarely makes a reaction spontaneous. This term frequently makes a reaction spontaneous. So that's why the color coding of red and green to say this usually is not spontaneous, this usually is spontaneous. How do you know if it's going to be in this specific case? So at a low temperature, if we have a reactant Gibbs free energy and a product Gibbs free energy on a plot. So the reactant shelf is lower than the product shelf. So products minus reactants, big number minus small number, we're going to get a positive delta G value. So that reaction is non-spontaneous, reactants to products. However, products to reactants is a spontaneous reaction. So we would say that reaction is non-spontaneous in the forward direction, but spontaneous in the reverse direction. Not trying to be confusing. If we go through and increase the temperature, it changes the value of the reactant and product's Gibbs free energy to these. Both shelves moved. Reactants went a little lower, products went quite a lot lower. The reaction is still non-spontaneous at that point because products are still higher energy than reactants. At this point, where reactants and products have exactly the same Gibbs free energy, that means your Gibbs free energy is equal to 0. That point is called equilibrium. Because we are talking about an endothermic reaction, this particular point could be called the melting point or the boiling point, the melting temperature or the boiling temperature. We're going to call it melting because in a minute we're going to talk about freezing, just for clarity. So if this is the melting temperature of a specific system, everywhere below that melting temperature, the reaction is non-spontaneous. And you got it, everywhere above that reaction temperature is spontaneous. The reactants are now higher shelf than the products. This down here says when Gibbs free energy is 0, that's equilibrium. You can solve for temperature. So you could actually determine what the melting temperature is, and that's delta H over delta S for any given system. So you can actually calculate the temperature if you needed to, but we're not going to do that here. Like I said before, everything below this temperature, non-spontaneous. Everything above this temperature is spontaneous. So right here where reactants are higher than products, you do get a spontaneous reaction. This is when delta H is positive and delta S is positive. Let's look at one more plot for the same case. Oh, no, before I go there, sorry. We say this reaction is entropy driven. That's because this term is the really important one that's going to help us decide spontaneity. What do I mean by that? This term says no, this term says go. So at the point where this term starts to win, where this term grows bigger than that term, that's where the reaction switch is flipped and the reaction becomes spontaneous. When this guy grows bigger than that guy, this term grows bigger than that term. So it's entropy driven. Okay, well, let's look at one more plot with the same set of conditions. Still positive and positive, delta H and delta S. So delta H is not really a temperature dependent reaction. So if we're plotting something, delta H versus temperature, there's a straight line, a flat line across my reaction, across my plot, because delta H does not really fluctuate much with temperature. You should note this is delta H as a function of temperature, not delta H multiplied by temperature. So if I'm plotting delta S versus temperature, or really the T delta S term versus temperature, at 0 Kelvin, it will intersect down here at 0. And because delta S is positive, it will have a positive slope if I plot that line. At that magical point where those two lines intersect, that's where delta G equals 0. That's where the switch is flipped, where the reaction goes from non-spontaneous to spontaneous. Temperatures lower than that delta G equals 0, non-spontaneous. Temperatures higher than delta G equals 0, spontaneous. Why is that the case? Again, we said this reaction is entropy driven. So when this term is the dominant term, this value is negative. Again, this is delta G as a function of temperature, not delta G times temperature. When this term is dominant, that's when delta G becomes negative. So if you just look at which line is more positive, delta H is more positive here, so delta H is the dominant term, non-spontaneous. T delta S is more positive here than delta H, so the T delta S bigger, delta G is negative. Okay, the other special condition was when we had an exothermic reaction that created order. So an exothermic reaction is negative, that creates order in the products is a negative delta S. We're going to say this reaction is enthalpy driven. Again, because enthalpy says yes, go, 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 and entropy says no, no, no. So this reaction is enthalpy driven. If we look at the same plots as before, reactants are higher enthalpy than products in this case. The reaction is spontaneous. Because this situation is different from before, this situation is spontaneous at low temperatures. If you increase the temperature, your shelves get closer together. You increase a little bit more, all of a sudden you're at equilibrium. Delta G equals 0. And just like before, that's an equilibrium spot, not the melting temperature this time, because delta H is negative. This is something like the freezing point, the freezing temperature. Because in order to freeze water, liquid water has to become solid water. Heat has to exit that system to freeze water. So this is our freezing point. At temperatures below the freezing point, the reaction is spontaneous. At temperatures above this freezing point, absolutely not. The reaction is non-spontaneous. So again, this is an enthalpy-driven reaction. It's all dependent on temperature. It's all dependent on enthalpy and spontaneous at low temperatures. Blah. So let's look at that same kind of plot we saw before. This time, though, enthalpy is a negative term, so our enthalpy line is below 0. Our delta S is also a negative term, so at 0 Kelvin it's going to intersect here, but it's going to be a negative sloping line this time. Oops. A negative sloping line this time. Just like before, at that intersection where delta G equals 0, this one is entropy driven. Dang it. Enthalpy driven. So when delta H is negative, when delta H is bigger than delta S, when this delta H is bigger than this T delta S term, that's when, scratch that, start over. When this negative, When this delta H term is more negative than this T delta S term, that's when the reaction is spontaneous. When this delta H term is more negative than this T delta S term, that's when the reaction is spontaneous. So over here it's spontaneous because this one is more negative. Over here it's non-spontaneous because this term is more negative than that one. Whew, that was painful. So one thing I want to point out before we move on to the next thing, you're going to encounter a table like this in the ChemActivity you're going to do. In this table, I want to point out these last two columns over here. In these last two columns, H minus T delta S, so that's delta G. Delta G is negative, 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 positive, positive. So hopefully you recognize that that means spontaneous, 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 non-spontaneous, non-spontaneous. Check out the K values. Remember what K values are? That's equilibrium constant. You thought we were finished with equilibrium constants, but we are not quite. So when the equilibrium constant is greater than 1, that means you have more products or reactants, more products. So equilibrium constant greater than 1, more products, greater than 1, more products, greater than 1, more products, less than 1, more reactants, less than 1, more reactants. So we said delta G tells us this is non-spontaneous. K tells us we've got more reactants. Yep, that better always agree. So there's a special relationship between G and K, and it's this equation. Delta G equals negative RT ln of K. So now we have two equations for delta G. Delta G equals H minus T delta S, and delta G equals negative RT ln of K. We'll see more with this RT ln of K equation soon in the next activity.